In this last series of videos, we're going to be looking at the relationship between shear and moment and the distributed load as a function of x. So if we look at this beam and we take a little slice out of this beam, we can see and draw the free body diagram of this beam. We see a few things of interest. One is on the left side we have our shear moment and normal force, and on the right side we have a shear moment and normal force also. We're just going to basically concentrate on the shear and moment at this time, but we see that shear due to this distributed load increases on the right hand side by some amount delta V, and on our moment will also increase by some amount delta V, and we can calculate that and find all that based off of this distributed load times this small sliver delta x. This delta x is just this very small piece, so if we find the area under this small little piece of curve, it's just a delta x times the distributed load. So if we look at summing forces in the y direction, we see that if we follow along up here, we will see V is our shear on the left-hand side minus the shear on the right-hand side minus the delta V, and then we have the distributed load force also. If we look at this, we see that the shear will cancel out. We can divide by this delta x, and we get a relationship of this delta shear divided by the length is equal to a negative of the distributed load. Okay, so if we take delta x and as it goes to 0, we find that dv dx equals a negative w, or distributed load. Now if we take a moment and we look at the moment, we see on the left-hand side we have a negative moment, and the right-hand side we have this moment plus the delta moment. And then we have the moment due to this distributed load, or actually first the shear itself, which is a negative moment about point A due to this shear force, and it's times its moment arm of delta x. And then we have the moment due to this distributed load. Here's the force of it, and here's the moment arm delta x over 2. If we look at this, we can eliminate our moments and rearrange the equation and divide by our delta x, and we end up with this equation here. And as we take the limit of delta x as it goes to 0, we get the derivative of the moment per x, some distance x, equals the shear. And if we take the derivative again of that, we find that we get back to our distributed load. So what does this all mean, right? Let's take a look at what this means for us. If we look at the equations that we have here, we found that this dv dx is equal to a negative w. What that is telling us is that the slope of the shear curve, the slope of the shear v, is equal to the negative of the distributed load. This is a great piece of information that we will use to help us draw our shear and moment diagrams. The other one is our slope of the moment curve is equal to the shear. This will also help us draw our moment diagrams. Last, if we rearrange these equations, we see that if we integrate these equations, we will come up with these two equations here. The first one is finding our shear. If we know our force or distributed load as a function of x, we can then solve for our shear. This value of v sub p is at some known point, and usually it is 0. Sometimes it could be the reaction force that we may have at the left-hand side of our beam. Same here with our moment. If we know our shear now, right, we can take this shear equation that we have and integrate that, and we can find our moment. So just a few comments about this. Again, our expressions of dV dx is equal to a negative of the distributed load. That's telling us that we can find the slope on our shear diagram is equal to the negative of the distributed load at some point x. Then we can find the slope of the moment diagram is equal to the shear at some point x. These are great expressions to know, and we also know that these ordinary differential equations can be solved by integration, giving us, of course, the shear itself and the moment itself. And again, we usually choose P to be a convenient location where the shear and moment are known and can easily be determined. A lot of times it's 0, especially for cantilever beams. If it's a simply supported beam, then this V sub P usually has the reaction force. And last, it says that rather than using the definite integrals above, we may use the indefinite integrals as shown here. On this approach, constants of integrations are obtained with the corresponding points of V sub P and M sub P. Let's now take a look at an example. Okay, so in this example, we have a cantilever beam for a shelf in a store, supports 160 chocolate candy bars. Each candy bar weighs 1 pound. I say yum. 1 pound candy bar. That sounds good to me. That's fun size, not those little teeny things that they call fun size. Anyways, these bars are stacked about 3 times as high on the right-hand side as they are the left-hand side. The distributed load turns out to be this equation. If we look at it, our distributed load W is equal to 4 pounds per inch times 1 plus x over 10. If we don't believe that this is correct, we know that at x equal to 0, we see that we'll have 4 pounds. And then if we take x equal to 20, we see we will have 12. So it is, again, meeting a requirement of 3 times on the other side. So 4 pounds on one side, 12 on the other. We are also given our reaction forces at B. We don't need to solve for those. Those are given to us also. And it makes sense that By is 160 because we have 160 pounds of candy bars. The last is to determine the shear and moment as a function, as functions of position, and draw the shear and moment diagram. Okay, so here we have our essentially our free body diagram on the right. I've set up the 2 graphs below it. Again, it's good to line that up so you can see these relationships between the distributed load and also the shear diagram and the moment diagram. The distributed load is given by that equation. We could think of it as a linear line. Okay. One thing we know next is that we can find our shear by using this equation here, which is just the integral of the negative of the distributed load. So let's do that. Okay, I'm going to rewrite this equation. I'm going to zoom in here a little bit. Our distributed load is equal to 4 pounds per inch plus 0.4 x. And now I'm going to integrate that. So again, the shear is equal to the negative of this, going from 0 to 20 of 4 plus 0.4 x dx. And if we integrate that, we get 4x. There's a negative on the outside of this. 4x, 0.2x squared, evaluated from 0 to 20. So if I evaluate this again from 0 to 20 at x equal to 0, our shear will equal 0. At x equal to 20, our shear will equal 160 pounds negative. Next, we want to integrate and find our moment. So m is equal to, again, the integral of v dx. We are going to be integrating from 0 to 20 of a negative 4x plus 0.2x squared dx. M equals a minus 2x squared, and then minus 0.0667 x cubed. And we'll evaluate that between 0 and 20 at x equal to 0. Our moment equals 0. At x equal to 20 inches, our moment equals a negative 1,333 inch-pounds. Now we want to take a look at how this plots on our graph. Okay, so it starts out, for our shear, it starts out at 0, and it goes down to negative 160. So some value over here. So if I look at this, I know that this is a quadratic equation. The question is, how is the slope? Because this thing could take a number of different curves for us. This thing could go something like this. It could go like this. So how do we know which one it is going to be? The way we determine that is, if you remember, I talked about this slope. The slope of the shear is the negative of the distributed load at that location. Right here at my point A, right at 0, we know that our slope is 4 pounds. And it's a negative, so our slope is a negative 4. This value is 4, and this value up here is 12. So my slope is going to be a negative of that, meaning that it will start out with a negative slope, and it gets more negative to 12. So it will have a slope something like that, where this value down here is minus 160. My slope here is equal to a negative 4 based off of this value. And then the slope here is equal to a negative 12. It's a negative of the distributed load. Next, we want to plot our moment diagram. We see that it starts out at 0. And it goes to a negative, very negative value of a negative 1,333. Okay. Again, we don't know if it goes like this or how it goes, or if it goes this way. So how do we determine which way it goes? So we can determine the way that this moment diagram goes by looking at the slope of the moment. And the slope of the moment curve is determined by the value of the shear diagram at that location. So if we look at x equals 0, the value of the shear at this location is 0, so my moment is 0. The value of the shear at the end, at B, is this negative 160, so it's going to be a very steep slope. So with that information, we can then draw our curve. And this will be this negative 1,333. And again, the slope here is equal to 0, which is a horizontal line, and the slope here is equal to this negative 160. So let's just do a real quick recap of this problem, because it's very significant for us to know this information going forward. One thing is that we notice that if we have a linear line like here, this is linear, that this one, so this is linear to the power of 1. We know that this is going to be power of 2, and this will be 3. So linear, quadratic, cubic is the relationship of our curves because of this integration. We also know the slopes of these lines going forward from the shear on down. The first one is, if we look at the slope of the shear curve, it is the value of the negative value of our distributed load curve. So it starts out at negative 4, so we have a negative slope here, and it ends at negative 12. And as we go along this, you'll see that slope will decrease more and more. Likewise, the slope of the moment curve can be determined by the shear curve. So the shear at 0, at x equals 0 is 0. That value is 0, so this slope is 0. The value at the very end is this negative 160, which is this value down here. And those slopes will tell us the shape of that curve. So finally, to wrap up, what approach should I use? Should I use the cut method of finding our cuts? Do we use that equilibrium approach, or do we use the integration approach? So in section 8.2, we looked at this equilibrium approach, and that's very robust. It always will work for us. We have to make sure that we draw the correct free body diagrams. There's no algebraic errors, and it will always give us the correct results for shear and moment. Also, determining these equivalent forces in free body diagrams when this distributed load is constant or as a linear function is pretty straightforward. If more than that, it gets a little more complicated. If our equation is cubic or things like that, then it gets a little more complicated. And it also can be very tedious if there's numerous different points, forces, and moments applied at the beam. It can become rather tedious. The integration approach is best suited for problems that have a single function of our distributed load that spans the entire length of the beam, like the example we just did. It's good also for complicated functions of Wx. It can be easily treated through integration, but there are some subtleties when the integration, using integration, we have point forces and things like that. It gets to be a little more complicated. This approach becomes more tedious, again, if there's more different functions of W as it spans the beam, and if there are numerous point forces. So they both can become tedious at different times. The integration approach and the equilibrium approach can be used also in combination with each other.